Noah Petro, Lunar Reconnaissance Orbiter data in support of characterizing future landing sites. Thank you, Noah.
Thank you. All right. Thanks, everyone. I was glad that Greg, in his introduction this morning, mentioned the passing of John Young, so I wanted to start with the beautiful oblique view of the Apollo 16 landing site taken by LROC, and we're going to play everyone's favorite game is Spot the Descent Stage. You've all seen it now, right? It's indeed there. The shadow of the descent stage is visible in this oblique, and I encourage everyone to explore this and all of the other wonderful LROC images of the lunar surface, not just places that we've been, but places that we're going to go in the future. And so what I'm going to do today is first give a little bit of an overview of where LRO is at right now. Physically, LRO right now is orbiting the moon. We're passing just to the west of the Austral Basin, approaching the South Pole. But also talk a bit about where the mission's heading over the next few years. And then I want to give an overview of the different data products that LRO has produced in support of future exploration. You're going to see many of those products used in the next few days, so for some members of the lunar science community, this will either be redundant overview, hopefully there'll be some news, but also for folks who maybe not are familiar with some of the products that LRO has produced, an opportunity to dig a little bit into what we have and offer for supporting future landing sites. Okay, so just a bit of an update on the mission. LRO is doing great. As I said, we're flying over the moon right now, approaching the South Pole as we speak. The spacecraft is healthy, it's doing really, really well. The instruments are all nominal. We have had no real significant degradation over the course of this current extended mission in any of the instruments, and so we're really quite pleased with the state and health of the spacecraft now and also the future prospects of the mission. I want to point out also that sort of the human aspect of the mission is really exceptional, both the operations team of the mission, but also each of the instruments. It's quite an amazing team of people, some of whom have been working on this mission now for over 10 years and continue to do so with the passion of a brand new mission, and I think it's to them that we owe a great debt of gratitude. I'd like to mention that we've been doing lunar science at the moon, or at least in the vicinity of the moon, for over 3,000 days. That's 103 lunations. So this baseline of measurements that LRO offers has been an incredible data set that really has, I think, led to significant improvements in our understanding of the environment at the moon. The sharper view of the surface and its environment has really led to a new era of lunar science. A few bits and pieces of news. Mini-RF is now, as I'm sure many people are well aware, has been restored to operational status. We're collecting data with the Goldstone antenna, which was a new measurement approach that Mini-RF has employed during this extended mission. As everyone well knows, there was a major hurricane that took out the Arecibo telescope, which was Mini-RF's main signal source for a number of years. They're now getting back up online, and we hope to be taking measurements with them in the not-too-distant future. At the end of the month, there'll be a lunar eclipse, which for a spacecraft that relies on the sun to recharge its batteries is, of course, something that we take note of, but we have a well set set of parameters for going through the eclipse. As a note down the line, October 20th is International Observe the Moon Night, which has been an event that our outreach and communications teams, with the help of Survey and the LPI, has turned into an international event to get people out looking at the moon, talking about the moon, and embracing the moon. So I encourage folks either at academic institutions or other facilities that can support events to really look into ways to engage with that and get the public excited about the moon. Currently, we're 44% of the way through a 3-year extended mission. As folks may be aware, originally LRO was extended for 2 years, and as part of the recommendations of the National Academy study, NASA's getting onto a 3-year cadence for extended missions. Yeah, you and me both, Clive. So we're going to be going through the process of extending for that 3rd year in the spring of this year. So that's an exciting opportunity for LRO to not just continue for a 3rd year, but also start looking further down the line at operations for 3 more years. Okay, this is, again, a little bit of folks who have seen me give these talks are familiar with these sorts of slides. But I do want to remind folks that LRO's orbit has changed over the life of its mission. Early on, we were in what we've called a quasi-stable orbit for commissioning, and I'll attempt to use the pointer, which gave us a chance to kind of stretch the legs of LRO. We went into a roughly 50-kilometer circular orbit for almost 2 years, for just over 2 years, which is our main science phase. And in the first year of that, we were an exploration mission. We transitioned to a science mission, and subsequently in 2011, at the end of 2011, went into this quasi-stable orbit. This helped us reduce our fuel consumption, which I'll talk a little bit about in a moment, but also brought us a little bit closer over the South Pole, but much higher up over the North Pole. This enables us to basically extend the life of the mission by reducing our fuel consumption. I want to point out that Grail data has been very useful for us to help plan our operations and really has minimized some of our uncertainty in the orbits. We've talked about LRO being a polar mission, but of course, as the moon processes under us, the poles moved away, or we've moved away from the poles. We now trace this bald spot over the south and north poles, which extends out, we pass about 87.5 degrees of latitude. This really is a benefit of science. As much as we moved away from the direct South Pole, we really have densified our coverage in this annulus around the South Pole. So just as a reminder, I've mentioned now a few times, LRO is a long-lived orbiter. We're in this new era of observing the moon. As opposed to being at the moon for 1 or 2 Earth years, or years, we're now there for over 8 years. This has offered us the opportunity to detect surface changes. Most notably, I would say, the detection of new impact craters as identified by the LROC NAC instrument, as well as other instruments as well. Some of the larger craters are now becoming visible in or evident in some of our other data sets. Our radiation instrument, the crater instrument, has been able to measure some unusual solar energetic particle events, particularly the one last year. The LAMP, crater, and LEND instruments have been able to make repeated measurements of the volatile the volatile content of the surface, and actually being able to see slight changes to that content, slight possibilities of either variations, diurnal variations, as well as multiple measurements by diviner to really reveal some really distinct thermal properties of the lunar surface that repeated measurements offer us. Having been at the moon now for several years, we're able to interact with other missions. Of course, early on there was LCROSS. While Laddie and Grail were in lunar orbit, we were able to interact with those teams, and now, of course, Artemis at the moon as well. We're able to interact with those missions, and we look forward to the opportunity to work with other missions that either orbit or get to the moon. Several of our instruments have employed new observation strategies, which, again, would not have been possible in a short-lived mission, and this gives us a real opportunity to make some new and important observations at the lunar environment. And of course, perhaps most importantly, is that we've now come back to this new initiative of returning to the moon, and so LRO has gone through now 2 cycles of interest in returning to the moon. So what's the future of LRO? And we operate on the 4P principles, and for those of you that know me, that does not stand for Porter, Pilsner, Pale Ale, and Pitchers. Personally, but not for the mission. So first and foremost, proposals. As I said, we're in the midst of our current extended mission, which, given this 3rd-year extension, will end on September 15th of 2019. And we're going to be in the process of planning for the subsequent extended mission proposal. Papers, the science team and the community has been incredibly productive with the use of LRO data. That's one of the great metrics, and so of course, we encourage members of the LRO science team to use LRO data, but also members of the community to embrace and use the LRO data to show, which, I mean, we've proven, I think, in spades, the utility of LRO data. This is a plot of peer-reviewed publications from the LRO science teams in red and the community in blue, this sort of explosion in use in our data over the life of the mission. That's a really important metric, and so, again, I reach out to the community to not only use our data, but also work with us to let us help you use our data in your papers. And then perhaps the most functional parts of this is the propellant on LRO. We currently have approximately 27 kilograms of fuel remaining. We have about 5 kilograms included in that for line loss. We've used about 20 kilograms in the last 6 years. As I said, we've been in this quasi-stable orbit, which has really allowed us to minimize the use of fuel. As a reminder to the maybe not that distant past, but the past, we launched with just shy of 900 kilograms of propellant. We used 82.5% of that to get into lunar orbit. So from that, we used a certain amount to do that first roughly 50 kilometer circular orbit. That was a very fuel-intensive orbit, which is why we went into this quasi-stable orbit. We had allocated a 6 or roughly 7% for science mission and its margins. But right now, we have about just under 50% of that fuel remaining. And so with good fuel practices on the spacecraft, pretty much, essentially the reduction in the number of major burns that we do, we may be able to extend the lifetime up to roughly about 11 years. There are certain operations that require fuel, momentum unloading, which requires fuel on the spacecraft. But if we go into this conservative mode, we may be able to extend the lifetime of the mission much longer. And then, from here out, 11 more years. And lastly, power, of course, is a solar-powered spacecraft. We are monitoring the health and status of the solar panel and the batteries, but everything looks to be in excellent shape for making the most of the time that we have at the moon. So let's talk a little bit about the data. And again, you're going to already have seen a number of examples of LRO data sets. I'd like to use, for the purposes of this portion of the presentation, the LROC expression, the LROC, which is much better in Latin on the LRO logo, but science enables exploration and exploration enables science. As much as LRO is a science mission presently, all of the data we collect have direct implications for the future exploration of the moon. So I'm going to be talking a little bit about some of the products that have been created that are wonderful science products, but also very useful for directing future exploration. The wide array of data that we've collected characterize the surface in really a number of ways, whether it's regolith properties, rock abundance derived from diviner, or as Brad showed, the direct identification of boulders in LROC, volatiles, lighting conditions, so on and so forth. As our mission has evolved, the quality and the granularity of the data is improved. As a kind of coarse example, this is a visualization produced at the Visualization Studio at Goddard. In 2011, this is a visualization of the Tycho crater using the then available LOLA data. At the bottom is a comparison of what's possible using the new joint Kaguya-LOLA data product as well. Our data products have continually improved with the life of the mission. And so whether you're looking for resources, characterization of landing sites, or even planning traverses, we offer a suite of opportunities to do that. So just to talk a little bit about some of the materials or the data sets that are available for characterizing the surface, we're all familiar, hopefully at this point, with the amazing power of the narrow-angle camera, 50 centimeters per pixel from our 50-kilometer orbit. There's the WAC data set, which should not be ignored. It's an incredibly valuable tool for not only characterizing broader regions, but also some of the UV characteristics, the compositional characteristics of the surface. The diviner data set, invaluable for identifying rocks, rock abundance, as well as the surface properties of the uppermost regolith. Paul Haynes' recent paper shows that quite well. And I just want to remind folks that I know that the rock abundance maps have, should not be used as something to be fearful of. Oh, we don't want to go where the rocks are. There's a very small white dot right there. That's a Surveyor 7 landing site. The rock abundance map should not be used to find places we shouldn't go, but to say, well, let's go to a place that has some real interesting diversity. I'll talk a bit in some length about the topographic products, particularly the high-resolution topographic data products that we get from the NAC. But we have incredible context from the LOLA product as well as this joint LOLA-Kaguya product. All of those topography products, of course, tell us something about slopes, the terrain ruggedness that Brad highlighted. We can use those for polar illuminations and, of course, calculating Earth line of sight. So just as an example of that, this is some material the LOLA team has produced, and it's available in the PDS. These are for both poles Earth visibility over the course of an 18.6-year cycle for both the north and south poles. This is obviously quite useful for identifying not just locations that you might want to go for short duration missions, but for longer period missions with line of sight to the Earth. This is pulling off of that a little bit, but also looking at areas that receive quasi or near permanent illuminations. We haven't, or solar illumination. We haven't found any areas that receive full illumination over the course of a lunar day, but areas that receive extended periods of illumination. And that leads to a really nice product that the LROC team has produced that incorporates the illumination conditions as well as some of the information we have about the surface to make estimates of trafficability and surface navigation, essentially following the sun as much as possible over a traverse along the rim of Shackleton Crater. And that was highlighted in a paper by Emerson Spire a few years ago. This is I guess at this point, recent, it's still last year, but relatively recent paper by Sato et al. In the ICRIS special issue of LRO Science Results, estimates of TiO2 abundance using the WAC data set. And so this is a product that's, or at least the multi-band mosaics are available from the LROC team. I encourage everyone to use those products and of course explore the paper, but for any investigation that wants to look at resources or exploring Mare surfaces, this is of course an incredibly valuable product. The Diviner team has a number of derived parameters of regolith properties. This is a really nice paper by Jean-Pierre Williams, also from last year, looking at multiple thermal properties of the surface to derive some different characteristics of the lunar regolith. And so I would, again, encourage folks who are considering lunar surface missions, landed missions as we're talking about here, to explore all of these data sets to characterize the surface that you're exploring, or use these products to identify where you might want to go. The LAMP instrument has gone into a new mode of operations. They opened their fail-safe door, which basically allows them to make higher spectral resolution, not higher spectral resolution, but get more signal to characterize the volatile content of the lunar surface. They did that as part of this current extended mission, and so that's a new product that they're generating. Again, this is material, or at least a data product, that will be useful in conjunction with some of our other products to characterize the volatile content of the surface. So all of these products I've talked about, or many of these products I've talked about, are available through the PDS. Hopefully everyone is got the Quick Map tool bookmarked and goes to it all the time. I know I do. But as a way of exploring some of the different data sets that we have from multiple instruments, not just LROC, it's a really valuable tool to seeing what we have, where the current extent of those DTMs, those digital terrain models, are, is perhaps one of the most important things in considering future landing sites. As Brad showed, we have a number, but if we don't have that DTM for your landing site, we need to, would request that you make that inquiry to us sooner than later so that we can get those into the queue. And again, all of these data sets are updated over a regular cadence. Just as a sort of a reminder, LROC produces an incredible array of different products from their narrow angle camera. The oblique images, as you've seen, provide an important context. The stereo products are really critical for evaluating the surface. And then these wonderful featured mosaics stitched together to provide nearly essentially seamless views of larger areas rather than just the individual strips is really important for characterizing, I feel, for characterizing landing sites. So just to talk a little bit about the DTMs and the quality of the DTMs, there's a paper by Henriksen last year that goes into the background of how it's done. Of course, we have the wonderful global context from Lola. We can place these DTMs into that context so that they're merged, essentially. I wanted to highlight an example of the Apollo 17 landing site. This is a mosaic of multiple DTMs stitched together, characterizing the entire valley. Just as a reminder of the real quality of these data, this is of course, on the right is a sort of a animated GIF or GIF, depending on your persuasion, of multiple images. So ultimately, to do these DTMs, you need at least 2 overlapping images acquired on consecutive orbits, ideally, to produce a product such as this. This is the NAC DTM of the landing site, and it doesn't blur out here, but you can see the topographic expression of the descent stage on the surface. Not only is it obviously, of course, visible, but it's apparent in the topography as well. The topography of geophone rock is apparent in the DTM as well. And so I like to highlight that as the utility and the real resolution, the resolving power of these amazing data sets. Okay, so lastly, LRO is the gift that keeps on giving. As I said, we're planning our next extended mission, ESM-4. We are evaluating multiple orbit, or at least multiple orbit options that will enable new science. We are very eager to support future landed missions. This image has appeared now twice. We should do a game of how many times can you see the same LROC image in multiple talks. This is the featured image from yesterday. This is the central peak of Jackson Crater, and it's just stunning. There's no other way to describe it. It's an amazing picture. Having looked at Jackson in Clementine data and other data sets, to see it like this is just unbelievable. Let's get back to the moon, and let's do it soon. With that, thank you.
Time for a couple of questions for Noah.
I just answered everything. That's great. Uh-oh.
Apart from, yeah.
Nor have you figured out, or has Mark or somebody figured out how we can put into published literature some of the three-dimensional information that comes from the NAC pairs?
Well, all those DTMs that are produced by the ROC team are made available through the PDS. That's the
Well, I know they're available, but how do you publish a three-dimensional, high-resolution picture like we use to identify the fissures in the sculptured hills and things like that?
I mean, apart from including a little CD-ROM or a thumb drive in every issue of Icarus, you know, their archive in the PDS or on the LROC website is the way that data is shared.
Some journals can take electronic data like that.
Absolutely. I mean, yeah, including it as supplemental material, but certainly getting the community to use the data is something that I'd love to see. Mark.
Answer a little bit of that, Jack. We are actually right
Use the
now-
microphone, Mark, please. This one should be good. No, not everybody online can hear you. Oh, you lazy kid.
Shut up the meeting. We're actually in the process of making old-fashioned topographic maps you can print out on paper where their contours overlaid on base maps. The first set are going back and looking at the Apollo landing sites, and we will produce such products for other places on the moon as the science community requests them, be them purely for scientific analysis or for landing site analyses. And the beauty of it is they're layered products, so you can just choose which base map that's underneath it that you want. Do you want the image data? Do you want, say, diviner data? What do you want? And then you could print it out yourself. We certainly can't print out all 7 layers or whatever and distribute them to everybody. But we will have products like this available at LPFC, samples, paper copies you can walk away with. And it's a big issue, right, to get that reduced down to a format that multiple people can use for multiple reasons.
Thanks, Mark. We really did come up with some interesting stuff looking at the NAC stereo, high resolution, and it's just a little hard to represent in a publication.
Sure.
Yeah, Jack, just to put on my GGR Planets Associate Editor hat here, certainly encourage submission of materials to supplementary information. That's a great way to archive data and link to it from your paper so that people can go directly to the data products and look at them. We don't have this capability yet, but there's other journals such as Geosphere, which you can put movies directly in the publication, and you could imagine a movie of a 3D data set where you could kind of move around or fly around. And so there are ever increasing ways of doing these things. Some journals are a little bit better at it than others right now, but I think we're all getting better at it.
All right. Thank you, Noah. Thank you, Tim and Jack.